Okay, so we are back here for the second lecture on the chemical basis of life. So this lecture, we'll probably run through this lecture a little more rapidly, mainly because I know that many of you have had most of this in 181 when you took Bio 181. I know that a few of you may have been a few years, and so some of this may not be as fresh in your mind. If I'm going through it really quickly and you're kind of feeling a little bit lost, please either email me or you can set up a time to chat with me as well, and we can do that. So please make sure that, if you don't understand a concept, that you reach out to me, because many of these concepts, as you're going to see, are going to come back later on throughout the semester and also throughout Bio 202. And the reason being is that chemicals compose your body, right? So when we're talking about human anatomy, your body is composed of chemicals. And all of these physiological activities that go on in your body have chemical reactions behind them. So it's really important for you to understand the fundamental concepts of chemistry, to be able to understand the language of chemistry, so that way then you can understand these physiological reactions that are occurring that make the body run, right? And so, there's chemistry in our movement. When we contract our muscles, you're going to see that there are chemical reactions that have to occur to allow muscle contraction to happen. Digestion, there are chemical reactions that have to occur, breakdown reactions that have to occur to break down that food into these, basic chemicals that we can actually absorb and then use to build things like proteins and nucleic acids and fats and things like that. Again, pumping of our heart, the nervous system, there's all of these physiological processes that have chemical reactions behind them. So we have to understand some basic chemistry to move on with the rest of anatomy and physiology. And so to go back to the very basics, remember that we're going to talk about matter. And matter is anything that has mass and occupies space. So matter is kind of like the basis of chemistry, right? And when we think about matter, anything that has mass, has atoms inside of it, and occupies space, it's easy to think of the things that we can see and we can smell and we can feel. So for example, if you're holding a hamburger in your hand, right, you know that it's matter because you can see it, you can smell it, you can feel it. But some of the things that might be a little more obscure for you in terms of what is matter would be things like the air around you, right? So the air around you is matter as well. It has mass and it occupies space. And we know that it has mass because it has things like oxygen atoms and nitrogen atoms and carbon dioxide atoms. And all of those atoms have mass. We know that it occupies space because we can compress air, right? Because it's a gas. So we know that it takes up space because we can actually compress it. So again, when we talk about things like matter, it may be, a little more obscure sometimes than what might initially come to mind. Now, when we're talking about mass, when we're talking about literally the atoms that make up an organism, that's mass, right? How many atoms are making up that organism? The mass of an object is not going to change, whether or not that mass is on Earth or on the moon, right? The number of atoms that make up you are not going to change depending on whether or not you're on the Earth or the moon. You're still going to have the same number of atoms. So like in Star Trek, if you were in Star Trek and you could just automatically transport yourself to the moon, right? Your mass would stay the same, but your weight would be different. And the reason is that weight is actually your mass plus the effects of gravity, right? So here on Earth, we kind of consider weight and mass to be synonymous because we're not leaving Earth, right? So we kind of focus on that. But if you were comparing things between the Earth and the moon, weight would be very different because weight is going to take into account gravity on Earth. So your weight is going to be much greater on Earth than it is on moon, where you have, less effects of gravity on the moon, okay? So that's the difference between weight and mass. So again, your mass, the amount of atoms that make you up, is going to stay the same. But weight will vary depending upon, what planet you're on, right? But again, while we're here on Earth, we're going to talk about kind of weight and mass as synonymous, unless you're, again, going to another planet. Or you're going to put yourself into or an item into a situation where there's no gravity, okay? Now, when we talk about matter, we're going to talk about 3 states of matter: solid, liquid, gas. Okay. And so if you're taking a chemistry class, you might be talking about, these other more complex states of matter that don't fit these 3 categories, like plasma, not the plasma that's in your blood, but we're talking about like plasma with lava flows and things like that. We're not going to get into that here because we're going to be focusing on the human body. So because of that, we're really going to deal with these 3 states of matter. Again, solid, liquid, gas. Solid is going to have a definite shape and a definite volume. So you can think about a cube of ice, right? That cube of ice, before it melts, has a definite shape and a definite volume. That's not changing, okay? Unless it melts and becomes a liquid. Now, as it becomes a liquid, that shape becomes changeable, right? Now, the volume is going to stay the same, whether you pour, if it's 10 milliliters of water, whether you pour it into a graduated cylinder, that's a long, shaped cylinder, or whether you pour it into a flat dish, right? It's still going to be 10 milliliters of water, but the shape can change, okay? Now, if you were to take that 10 milliliters of water and put it in a pan and boil the water, and you evaporated that water into a gas, now your gas has both changeable shape and volume. So as you heat up those water molecules, they get excited, they take up more space. Okay, now your volume has changed. So again, as you go through these 3 different states of matter, they're going to have these slightly different properties. Now, we also have to talk a little bit about energy, and energy is very simply the capacity to do work or put matter into motion. And so we have to talk about energy because we're going to talk about how energy is used to do work with our body, right? Now, energy does not have mass, nor does it take up space. But again, it has this capacity to do work and put matter in motion. The greater the work done, the more energy that's going to be used. Okay? So when we talk about energy, we have these kind of basic 2 forms, right, that we're going to talk about. Kinetic energy, which is kind of your energy of motion, your energy in action. And then we also have this potential energy, which is your stored inactive energy. And so we're going to talk a lot about potential energy when we talk about energy stored in chemical bonds, this type of potential energy that we call chemical energy. And that energy is going to be stored in these chemical bonds. It can be stored in the bonds of glucose, or it can be stored in the bonds of something like ATP, right? Now, I know you're like, ATP, I sort of kind of remember that from my good old 181 days. So remember that ATP is something called adenosine triphosphate. It's the energy currency of our cell, and it has these high phosphate bonds. Don't worry, we're going to get into this again if you're, kind of just barely remembering this, but I like to introduce it now because this energy that's stored in those phosphate bonds is high energy, but those are high energy bonds. But this is stored energy, and when we break those bonds, okay, when we break up ATP, we can release that energy and then use that energy that was stored in those bonds to do motion, put that energy into action, kinetic energy. And so we can use it to do things like muscle contraction. So, you can use it to pull that pencil up off the desk, okay? So just to give you kind of, again, an idea of how kinetic and potential energy are going to work with each other. Now, that easily kind of brings me to my next point, which is that energy can be transformed from potential energy to kinetic energy, just like we talked about with the potential energy and the bonds of ATP being converted to this kinetic energy causing muscle contraction. So stored energy, again, can be released and result in actual action. And this is really a great little video. I'm not going to show very many of these videos. I'm going to just post most of them. But this one just happens to be a really great video. So I'm going to go ahead and let you listen to this one. Take off my pencil here. Sorry about that.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
So I like this video because it's kind of the whole package, right? It really does a good job of helping you understand potential energy, kinetic energy, the conversions from potential to kinetic energy. And then the next point that we're going to talk about, the fact that not all energy transformations are 100% efficient. And then it also combines that in the form of talking about cellular respiration, kind of reminds you a little bit about that. So anyway, it's a good video. If you can watch it again, I will post this video for you. It's really a great video. Okay, so when we talk about, again, energy, there are these different forms of energy. So when we talk about, there's different forms of potential energy, different forms of kinetic energy. And so one of the forms of potential energy that we could talk about is chemical energy. And that's this energy that's stored in the bonds of chemical substances. We're talking about the energy that's stored in things like ATP and glucose, right? There's energy that's stored inside those bonds. And if you were to break those bonds and that energy is released, then it can be used to do work, okay? So that's chemical energy. There's also electrical energy, which is going to result from the movement of charged particles, things like electrons, right? So that's another form of energy. And we'll talk a little bit about electrical energy in terms of when we talk about nerve conduction. We can also talk about mechanical energy, which is this kinetic energy, right? That's directly involved with moving matter. So here's kind of all these different examples of mechanical energy, right? Like you can use mechanical energy to ride your bike, right? Do cycling, to move the bike. You can use it to skateboard, okay? You can use it, right? Mechanical energy when you release that bow and that arrow moves through the air. So again, this is where we're directly involved in moving matter. And then lastly, there's radiant or electromagnetic energy. And this is energy that travels in the form of waves. So for example, heat, right? Heat travels in waves. We also have visible light. So the visible light spectrum is anytime we're talking about light, they're light particles, and these particles move in a wave-like pattern. And we know that that wave-like pattern, whether or not the wavelength is large or the wavelengths are smaller, right, is going to depend. So if we have large wavelengths or if we have small wavelengths, right, like this. Sorry, again, my drawing with a pen is horrible. But that will determine, right, what type of light we're detecting. So is it red light? Is it blue light? So that's part of the visible light spectrum. And try to keep in mind that when you're talking about something like plants, plants can do photosynthesis, right? So they can actually take radiant energy, right, in the form of visible light, and they can use that energy to actually make carbohydrates, to make glucose. And then they can take that energy and store it in the bonds of glucose. And then they can take that glucose when they need it and then break those bonds and use that energy to run the plant, to grow and do all the things that a plant needs to do. So again, I always say I would happily be green if I could do photosynthesis, if I could just go out and take in a little energy from the sun and then use that energy to make glucose, to store that energy in chemical bonds. It's pretty amazing that plants can do that. And they don't have to eat then, right? If we could do that, we wouldn't have to like stop what we're doing and take the time to eat if you're busy. Okay. So anyway, those again are these different forms of energy that we're going to talk about in terms of human anatomy and physiology. Now, we already talked about energy conversions, right? So energy can be converted from one form to another. So their example here was turning on a lamp converts electrical energy to light energy, right? But we talked a little bit about converting, energy, chemical energy, right? So potential energy stored in the bonds of chemicals like glucose. And then we can convert that to, kinetic energy used to do muscle contraction. So, again, when we talk about energy conversion, just like the video talked about, not all energy conversions is efficient, okay? Much of it is inefficient. And so some of that energy is lost as heat. And depending upon, again, what chemical and what energy conversion is occurring may depend upon how much heat is lost. So for example, when you're looking at an incandescent light bulb here, you can look and see that about 85% of that energy is lost as heat, which is why we consider incandescent bulbs to be much more inefficient, versus an LED light where you only have 10% of that energy lost to heat and 90% of that energy goes into the production of light. So again, how much of that energy is lost depends on the energy conversion. Now, that fact that energy conversion is inefficient isn't all bad for us, right? And that's because we are homeotherms, right? We like to maintain a constant internal body temperature, whether that be 98.6 or for some of you it might be slightly different. For me, it's more like 97.9. But my body likes to maintain that temperature. And if for some reason you are to get cold and your body temperature starts to drop, this fact that some energy is lost as heat is really beneficial. So you might start, shivering and your muscles are contracting. And as the chemical reactions that are occurring inside your muscles to allow them to contract are going on and ATP is being broken down, some of that energy is going to be released as heat. And we use that heat to help, again, bring back up our core body temperature. So this fact that some energy is lost as heat is actually quite beneficial for us homeotherms. Now, again, all matter is going to be composed of elements. And so we're going to kind of go back now and talk a little bit about these kind of building blocks of matter now that we've talked about energy. So when we talk about elements, elements are kind of how we are going to categorize matter. So elements are substances that can't be broken down into simpler substances by ordinary chemical means. So meaning if you have, again, carbon, unless you break that carbon down and pull out some protons, it's going to stay carbon, okay? And so all the carbon atoms that we have, if I have a glass of carbon atoms, they're going to stay carbon atoms. And carbon, they're going to be consistent with that carbon element, right? They'll all be part of that carbon element, unless for some reason you change the number of protons. And we'll get into that a little bit more in just a minute. So, okay, elements, again, are substances that can't be broken down into simpler substances by ordinary chemical means. Now we have 4 major elements, and you need to know these 4 major elements that make up the 96% of our body, because we're going to talk a whole lot about them. And so these elements are carbon, oxygen, hydrogen, and nitrogen. And so we like to refer to these as honk. And I think it's just the easy way to remember them, honk. So again, H stands for the hydrogen. The O stands for the oxygen, the N stands for the nitrogen, and the C stands for the carbon. So that's an easy way to remember these 4 major elements that make up most living organisms and for us, the human body. Now, there are lesser elements that make up about 3.9% of the body, and they're going to include things that are actually quite important, even though we have them in a much smaller percentage. So, for example, calcium, right? Calcium is very important, again, for our bones, right? And we'll talk about how that works. Also very important for muscle contraction. So we need that calcium for muscle contraction. Things like potassium, sodium, we need that. Very important for some of our nerve conduction. We can't have nerve conduction without that. Iodine, important for metabolic reactions because of our thyroid hormones. We need that iodine. Iron, important for, again, hemoglobin in our blood. So even though there's all these lesser elements, they're still very important in terms of the human body. And then we have about 11 what we call trace elements that make up less than 0.01% of the body. And the reason that these are so important is that they're required in really minute amounts, but they're required for enzymes, enzymatic function. So again, every reaction, and we're going to get into enzymes, we'll review enzymes at the very end of this lecture, but just to give you kind of a quick kind of refresher, enzymes are required for every chemical reaction that happens in your body. And so for these enzymes to function, some of them will require some of these trace elements and things, again, like, copper or magnesium or things like that. So some of these trace elements are really important for enzymatic function, and we need those. So you can see here some of these trace elements. You do not need, I just put them up here because I thought you might find it interesting. But again, you do not need to know these trace elements. I'm not going to ask you on a test, is silicon a trace element? Not requiring that. I just want you to know that there are trace elements and that they are required for enzymes. But that's it. So again, all of the elements that we have that are these building blocks, right, are going to be made up of the atoms. And atoms are really kind of the building blocks for each element. So, you can put together atoms, right, of the same element. So here's an oxygen atom, right? And we can put it together with another oxygen atom, okay, to make up a molecule. We'll talk about this in just a minute. But both of these oxygen atoms are part of the same element, oxygen, right? And so again, we're going to talk about what makes them oxygen atoms, okay? And what makes them the same element here in just a minute. So atoms are kind of these unique building blocks for each element, and they're the smallest particles of an element with all of the properties of that element. So these are really like, our atoms are kind of like, if you can consider, the bricks of the Lego world, okay? And we can put those bricks together with either atoms of the same element, like here, when we make up oxygen or O2, or we can put together these atoms with different elements, like when we make up something like water here. Sorry, my horrible writing. That's a hydrogen, if you can't tell, and there's another hydrogen there. So again, we're going to think of these atoms as kind of these building blocks, right? And so maybe all of the red blocks that you have are going to be oxygen atoms. And maybe all of the blue blocks that you have are going to be hydrogen atoms. And so all of the blue, all the blue Legos are going to be one element, and all the red Legos are going to be another element. So that kind of helps give you like an analogy on how to put this all together. Now, what gives each element its particular physical and chemical properties are going to be these atoms, and we're going to talk about what inside these atoms will make them one atom of one element different from an atom of another element, especially when we get into protons and electrons. So let's talk a little bit about the atomic symbol. Every atom of an element is going to be given a 1 or 2 letter chemical shorthand for each element. So for example, oxygen, again, like we talked about, is going to be given O. That one's an easy one, right? Carbon, C for carbon, super easy. But some of them, or calcium, right? Ca for calcium, pretty easy. But some of these symbols come from the Latin names and they're not so easy. So for example, sodium is given Na. So you might be like, where does that come from? That's nowhere close to sodium, right? But it comes from the Latin origin for sodium, which is natrium. Same with potassium. Potassium always throws everybody off because it's K, right? You're like, well, it should be P. But the reason that it's given K is that it comes from the Latin origin kalium. So just a couple of the atomic symbols are a little confusing. So here is the periodic table of elements, and the periodic table and how they're arranged, we're going to talk about is really quite helpful. But you can see here's always going to be the symbol, right? And then usually underneath they'll have the name. So you can see, here F is for fluorine. Again, like we talked about, O for oxygen, He for helium. And then we're going to talk about the atomic number here in just a minute, and then then we'll actually talk about the atomic mass, which isn't actually given on this one, but on most periodic tables it is. So let's see. When we talk about an atom, the nucleus is going to be kind of that central part of an atom. So this gets really confusing because we're going to also talk about the nucleus of a cell. But atoms have their own nucleus in the center of the atom. And that nucleus is going to consist solely of the neutrons and the protons. Okay? Now, neutrons, if you remember, are the subatomic particle that has no charge. And it has a mass of 1 atomic mass unit. Okay. Now, protons, if you remember, P for protons, P for positive, right? So protons have a positive charge and they have a mass of just 1 atomic unit as well. And then we have electrons. And electrons, because they are not, remember here, the nucleus only consists of neutrons and protons. Electrons are actually found orbiting the nucleus. And I'll show you a picture of this in just a minute. And those electrons are going to have the negative charge. So protons, again, positive. Electrons, negative. Neutrons, neutral. Oops, sorry about that. I'm drawing all over the slide here. So the thing about electrons, though, is you may say, oh, okay, well, neutrons have 1 atomic mass unit, protons have 1 atomic mass unit. What about electrons? Electrons are so tiny that they're virtually not considered in the overall weight. So we give them 0 atomic mass units. And that's because they are 1/2000th of the mass of a proton. They're so tiny. So we really don't even consider their weight. Now, that doesn't mean that they're not very important, because they are. They're very important in talking about how one atom is going to interact with another atom. So just because they're small does not mean that they're not mighty, okay? They are small, but they are very, very important in determining how atoms of one element are going to interact with atoms of another element or the same element. Okay, so when we talk about these atoms here, again, you can see the nucleus of the atom that's going to have our protons in red here, and then the neutrons in yellow. And then the electrons here are going to be orbiting around the nucleus. And so you can see we have these two different models. We have one that's called the planetary model, which is kind of drawn like planets orbiting, right? But here in the planetary model, we draw this more for simplicity, so you can see how many electrons are actually orbiting, right? So we can see we've got 2 protons, 2 neutrons, and then 2 electrons. But the orbital model will oftentimes show this electron cloud. And that's because really, if you could put this in 3 dimensions, right, those electrons are orbiting all around this area surrounding the nucleus. The orbital model kind of depicts more on how those electrons actually are orbiting. They could be found anywhere in this electron cloud at any point in time. But for simplicity purposes, of course, we like the planetary model because this makes it much easier for us to visualize. So we kind of will use the planetary model more often when we're talking about how these atoms are going to interact with each other. And if the atoms are electrically neutral, this means that the number of positive protons is balanced by the number of negative electrons, right? So here, and in this helium atom, we have 2 protons and we have 2 electrons. So again, this is going to be electrically neutral because our positive and our negative charges are balancing each other out. Now, different elements are going to contain different numbers of subatomic particles. And what's going to determine an atom of a certain element will always be the number of protons, okay? So the number of protons are going to determine, you're going to see here that sometimes the number of neutrons and the number of electrons can change for an atom of a certain element, but the number of protons will always stay the same. So what makes hydrogen hydrogen is that it has 1 proton, okay? Now, if it's electrically neutral, it will have 0 neutrons and 1 electron, okay? Helium, what makes helium helium is the fact that it has 2 protons, okay? If it loses 1 proton, then it automatically becomes hydrogen. So helium is helium because it has 2 protons. What makes it neutral is that it has 2 protons and 2 electrons that balance each other. And we'll come back to the differences in neutrons. Again, when we talk about isotopes, you might kind of remember that. Now, lithium is lithium because it has 3 protons, right? So it can have 3 protons, it can have 4 neutrons, and then 3 electrons. And if it has 3 protons and 3 electrons, then again, it's going to be electrically neutral. But what makes it lithium is that it has 3 protons. So identifying facts about an element include something called its atomic number, okay? And so its atomic number is the number of protons, because the number of protons tell you what element that atom belongs to, right? So it's so important that we give it a special name, the atomic number. Okay, now the mass number, we'll talk about in just a minute, is going to be the overall mass, atomic mass units, which remember each proton and each neutron has 1 atomic mass unit. Again, electrons are so small we don't count them in the mass. So we'll calculate those up. And then we're going to talk about isotopes and atomic weight here. Okay. So here again is just a planetary model. You can see of hydrogen, helium, and lithium, just showing you the different numbers of protons, neutrons, and electrons. And then again, we talked about the atomic number being the number of protons and nucleus. So again, the number of protons are going to determine, I don't know how much more I can say this, it's really important that you know the number of protons, okay, are going to determine which element that atom belongs to, okay? And it's always written as a subscript to the left of the atomic symbol, okay? So here, if you look, the atomic number here in helium is going to be written at the bottom left, and it's going to be 2, okay? So then we're given this symbol, and I said, how many, protons does helium have? 2. is the automatic answer. And then the mass number is always given on top. Now the mass number is the total number of protons and neutrons in the nucleus. And remember, we don't count the electrons in the overall mass because their atomic mass is so small. It's 1/2,000th of the proton. So it's so tiny. So our total mass of an atom is considered to be the protons plus the neutrons. So here, okay, in helium, you've got 2 protons and 2 neutrons. So that gives us an atomic mass number of 4. So it's written again as a superscript to the left top, the upper top left there. Okay, now isotopes, remember isotopes are going to be where you have an atom of the same element, meaning the same number of protons, right? So for example, here, these are all carbon, okay? So if they're all carbon, they all have to have 6 protons. That's what makes them carbon, right? But they're going to have different mass numbers, which means if the protons are the same, then the neutrons, because mass is protons plus neutrons, then the neutrons are what have to be different, okay? So these are isotopes of each other. So carbon 12 is going to have 6 neutrons. So 6 plus 6, right, is 12. Carbon 12, that gives it a mass of 12. Now, sometimes carbon can have 7 neutrons. It can have an extra neutron shoved in the nucleus there, and that makes it carbon 13, okay? And then you can shove another extra neutron in that nucleus. Although as you shove more neutrons in that nucleus of an atom, it does tend to make it more unstable. So carbon 14 here, okay, has a mass number 14, 8 plus 6, which means that it's going to have 8 neutrons. Because again, it has to have 6 protons to be carbon. So those are all isotopes. They're considered isotopes of carbon. Now, again, the atomic weight is the average of the mass numbers of all the isotopes that exist naturally. So when you see the actual mass number, it's oftentimes a decimal number. And that's because what they're going to do is they're going to take all of the different isotopes that exist naturally and then in their percentages, and they're going to take an average of those mass numbers based on their percentages. And that's what you're getting for the atomic weight, okay? So your atomic weight is just an average of the mass numbers of all of the isotopes that exist naturally. So again, here we're just showing you some isotopes of hydrogen. So you have hydrogen 1, which again has 1 proton and no neutrons. You have deuterium, which is going to have 1 proton and 1 neutron. So then it will have an actual mass number of 2. And then you have tritium, which is going to have a mass number of 3, and that's because it has 2 neutrons shoved in there. Again, the protons, as you can see, don't change. You still have 1 proton in that nucleus, okay? Now, why are isotopes important? We use isotopes for all kinds of things, and radioisotopes are really important because they're isotopes that decompose to form these more kind of stable forms. And as they do, they decompose, that atom loses various subatomic particles. And if it loses enough subatomic particles, including a proton, again, it has to lose a proton to become a different element, but that can happen, right? So that can happen in our decay, and we use that measure of decay to oftentimes age things. But what's important for us in terms of human anatomy and physiology the medical field is that we can use the rate of decay of these isotopes for medical purposes, and they can actually be detected and measured with scanners. So the nice part is the rate of decay of these radioisotopes is going to be stable, and we can use that in terms of medicine. And of course, I had to give Marie Curie some props here because she is the one that she's the scientist that discovered radioactivity, and ultimately was probably likely responsible for her death. But again, so this energy that's released as an isotope decays is referred to as radioactivity. And again, it can be detected and measured with scanners. So are radioisotopes beneficial? Sometimes they are, right? Because we can use these radioactive isotopes and their regular rates of decay that we can calculate, right, as biological spies in medicine. And so what happens is living cells can't really distinguish between radioactive and non-radioactive isotopes of the same element. And so because of that, because these isotopes share the same chemistry as their more stable forms of isotopes, the body will take them up the same. And we can use this then to diagnose certain diseases using PET scans and MRIs. So for example, if we were to give you radioactive iodine, okay, and your thyroid would take up that radioactive iodine just like it would take up any other form of the regular iodine that's not radioactive, and so it would take up that radioactive isotope just like it would take up the non-radioactive form of iodine to make the thyroid hormones. And there's a certain rate that we make thyroid hormones. Now, if your thyroid is overactive, it's going to take up more iodine more quickly, and it will take up that radioactive iodine more quickly. And so it will glow really bright, on a scan. So again, this is how we can use those radioactive isotopes to be quite beneficial for us. Now, radioactive isotopes can also be harmful, right? So radioactivity can also damage living tissue, and some types can actually cause cancer. So we know that from like Chernobyl, where we had, excessive exposures to lots of radioactivity, and it actually caused damage to the DNA and eventually caused cancer. Also radon from uranium decay in the ground can cause lung cancer. So that's one of the things, that's why we oftentimes test certain sites for radon. But also, sometimes the radioactivity can actually be used to destroy cancer. So we can actually localize that radioactivity and use it to destroy cancer. So again, all kinds of interesting uses for radioactivity and radioisotopes. Okay, so now I want to get into a little bit on combining matter and how we make molecules and compounds, because really we're going to use most of our chemistry when we're talking about certain molecules and compounds that exist within the body. So most atoms will chemically combine either with other atoms or with another atom of the same element to form things like molecules. And a molecule is just a very general term that we're going to use for two or more atoms that are bonded together. So for example, we can take an oxygen atom and bond it to another oxygen atom. And I'm drawing a double bond here because, oops, I'm sorry, I really did a botched job here. Let me try this again. So we can take an oxygen atom here and bond it, and I know they form a double bond here, so that's why I'm drawing it that way, to another oxygen atom, and we have O2, right? So that is a molecule. Now, when we take specific molecules that actually have an atom of one kind of atom bonded to another kind of atom, okay, we call those molecules compounds. So they're still molecules, but we also call them compounds. So for example, if you take an oxygen and you're going to bond it to a hydrogen here and another hydrogen here. So now we have two atoms. Oops, I'm sorry, I drew off the slide there, hydrogen there. Then we have a water molecule. Sorry, I know my pen drawing is less to be desired. But we have a water molecule here. And so a water molecule is also a compound because we have atoms of different elements, so more than one kind of atom bonded together. So we have an oxygen atom bonded to a hydrogen atom of a different element. So that's not only a molecule, but also a compound. Now, oxygen is a molecule, but it's not a compound because we have atoms of the same element. Make sense? So again, language, terminology. So when we talk about any two or more atoms bonded together, it's a molecule. If we're talking about those two or more atoms being different atoms of different elements bonded together, then we also make a compound. Okay, so our water molecule is also a compound. So molecules with only one type of atom, like H2 hydrogen or O2 oxygen, are just called molecules. But here, when you have something like C6H12O6, which, does anyone know what that one is? Oh, I give it away. Whoops. Sorry, I got it away. It is glucose, okay? And so that one is both a glucose molecule, and glucose is also a compound. So hopefully that helps out a little bit. Now we also have to talk a little bit about mixtures, and most matter exists as mixtures. So mixtures are when we take two or more components that are physically intermixed, and oftentimes it will be, liquid of certain molecules. So that liquid might be, water molecules, and then we might have, salts like sodium chloride that's intermixed in there. Now, we're talking about things that are being physically intermixed, right? So like you can stir them up and physically intermix the salt in the water. So there are three basic types of mixtures that we're going to talk about. We're going to talk about solutions. We're going to talk about colloids. We're going to talk about suspensions. And I had to include this sticker, which is just awesome, right? Chemists have all the solutions. Oh, come on. I have to keep you awake somehow. So here we've got the difference between a solution, a colloid, and a suspension. So a solution is just where we're going to have solute particles that are going to be dissolved in a solvent, which is usually our liquid. So these, and not always a liquid, but in many cases when we're talking about the human body, it often is. And so the solute particles are going to be really tiny, and they're not going to settle out. So if you sit that solution for a long period of time, the solute particles are not going to settle out. And also they're not going to scatter light. So it's not going to look any different to you. So for example, mineral water is a really good example of this. Your mineral water has water molecules, but also it has solute particles mixed in between those water molecules, things like calcium or magnesium inside there. And those minerals are not going to settle out. They're going to stay throughout the water, intermixed throughout the water, and they're not going to settle out or scatter light. And so you're not going to be able to see them. So that's a solution. Now, a colloid is going to be where you have solute particles that are a little larger than you would see in a solution. And so they are going to scatter light a little bit, but they're not going to settle out. So Jell-O is a really good example of this because, you mix the Jell-O, and once especially, you physically mix it in there and it dissolves. Those solute particles, you're not going to see them. They're not going to settle out, right? And you can even, again, put it in the fridge and make it a, more gelatinous material. But they do scatter light, so you can see the difference, right? And in this case, it looks more red, right? Because of the solute particles that are in there and how they're scattering light. Now, a suspension is where you have solute particles that are both large, okay, and settle out and scatter light. So here again, the solute particles are large, but they're not settling out, okay? They're staying in solution. Here in a suspension, they're large, and they settle out, and they scatter light. So they do all of the above, okay? And so we're going to use blood as a really good example of this. And so if you were to leave, blood sitting on a counter for a long period of time, you would see that it would actually settle out. It would kind of act as like a natural centrifuge. But you can speed this process up by using a centrifuge, and you can see that, again, the red blood cells are going to settle on the bottom, and then the liquid plasma will settle on top. So blood is actually considered a suspension. Okay, so this is just kind of going through exactly what we just talked about. Colloids are these emulsions. Again, we got these large solute particles, but they don't settle out, okay? But they do scatter light. They do scatter light, but don't settle out. And again, we talked about you can form this sol gel, this solution to gel transformation. And we see this in the form of Jello, which was our example, but also cytosol in the cell is actually kind of our natural colloid that we're going to talk about. And it is gelatinous inside that cell too. So cytosol is kind of like the jello of the cell. Okay, so it is a colloid. Now, when we talk about solutions again are these homogeneous mixtures, meaning that the particles are evenly distributed all throughout. And so our solvent is going to be the substance that's present in the greatest amount. And usually, especially in the human body, it's a liquid, and this liquid is water, okay, for the most part. So for the most part, when we're talking about solutions in the body, for the most part, our solvent is going to be water. Now, the solute is going to be the substance that's present in a much smaller amount, and this substance often is dissolved in the solvent, so dissolved in the water. And so an example of this would be, glucose in the blood. So that glucose is the solute, and your blood, especially plasma, is the solvent. So that glucose will be dissolved in the plasma. So again, most solutions in the body are true solutions of gases, liquids, or solids that are dissolved in water. So water is going to be our big solvent. Now, concentration of true solutions, three ways that we will express concentrations is percent of solute in the solution. So how many parts of that solute there are per 100 parts of solution. And the solvent, again, is usually water. So for example, if we say that we have like a 10% solution of salt, in the blood, which would be really high, but if we said that would be 10 parts salt to 90 parts water. Okay, so that's a 10-part solution. So, and anytime we do this sign, it's parts per 100. So, this is 10 parts per 100 parts water. Okay. Now, what's interesting is when you talk about something like salt water, let me see if I can actually use this here right a little bit better here. So if you talk about salt water is actually considered to be 35 parts per 1,000. So we write it like this, because this here means parts per 100 with 1 0 in the bottom, and this means parts per 1,000. So just kind of interesting. I teach marine biology, so I had to throw that in there. But anyway, most of the time we're just going to give percent of solute in a solution. Now, you can also, and we use this more for like medications and things like that, or sometimes we do it with like blood glucose levels, but you can also express things in milligrams per deciliter. So, and a deciliter, just as a reminder, is 1/100th of a liter, okay? So, for example, if we're talking about normal fasting blood glucose levels, they're around 80 milligrams per deciliter. Okay? You'll also sometimes see medications given in milligrams per deciliter. So we have 80 milligrams of glucose per 1 deciliter of water or plasma. The third way that you can see solutions kind of expressed is molarity. Molarity, I have a song for you that my high school chemistry teacher actually made us sing over and over again, and he told us we would remember the song for the rest of our life. And at the time, I was a teenager and I rolled my eyes. And the funny part is I still remember this song. And it goes, molarity, molarity, it's moles per liter of solution. You take the grams, convert to moles, and divide by liters of solution. So there you go. There's my molarity song for you to help you remember. You can sing it over and over again and roll your eyes at me, and then you'll remember it 2 years from now. It sticks in your head. I don't know why. So again, like the song says, molarity, it's moles per liter of solution. So number of moles of solute per liter of solvent. And if you're remembering what a mole is, not this type of mole, but 1 mole of a compound is equal to its molecular weight in grams. So for example, if you look at glucose, which is C6H12O6, it has, if you count up the molecular weight of all of the 6 carbon atoms and the 12 hydrogen atoms and the 6 oxygen atoms, the molecular weight would be 180.12 atomic mass units, or 180.12 grams. So if you take 180.12 grams of glucose and you added this to enough water to make 1 liter, right, per 1 liter of solution, then you would have a 1 molar solution of glucose. So remember, you take the grams, convert to moles, and divide by liters of solution. So there's my song for you. Just so that you know, 1 mole of any substance, as a reminder, always contains 6.02 times 10 to the 23rd molecules of that substance. So again, 1 mole of glucose is going to contain 6.02 times 10 to the 23rd molecules of glucose. And where do we come up with that number? That was Avogadro's number. Hey ladies, here, take my number here. So here's Avogadro's number. I'm not going to expect that you know Avogadro's number, but I just like to give you that as a reminder. I really more care that you know a molarity, and that's its moles per liter of solution. And so again, you would take, grams, the molecular weight here, and add it to 1 liter of solution, and that would give you that 1 molar solution. Now, molarities in the body can be really small sometimes. So they can be, 0.0001 molar, which is expressed oftentimes in millimoles, right? Because it's, 1/1000th of a mole. So you can have 1,000 millimoles equals 1 mole, or we can use millimoles, right? And it's just an easier way to express molarity. So you're going to see we'll use millimoles just as a reminder, so you know what that is when we get there. Now, the difference between mixtures and compounds. There are 3 main differences. And that is, unlike compounds, mixtures do not involve chemical bonding between components. So we're literally physically mixing things up, right? Mixtures can be separated by physical means. So you can, strain or filter them, such as, again, if you were, or you can use a centrifuge, right, to separate them. So for example, right, blood can be separated out. It's a mixture of the solutes and things that are in there, in the solvent. So we can separate that out by using a centrifuge, or letting it just, set for a long time. Mixtures can be heterogeneous or homogeneous. It depends, again, on your mixture, and compounds are only homogeneous. And we're going to talk about that because compounds, again, are going to be bonded together. So we'll talk about how we bond them together. So again, the big thing here is that mixtures can be separated. That's really the whole goal of the slide. And you can separate them by, filtering and sifting. Sometimes, again, you can let them settle like we did here. Sometimes you can evaporate off the water. For example, like if you have a mixture of a salt solution, you can evaporate off all of the water, and then you're left with the salts that are behind, right? Okay, we can separate things by chromatography, by the different weight of the different chemicals within it. So, all right, so now we're going to get into the chemical bonding of compounds. So let's go, we're going to go back down. Mixtures are kind of at a larger level. We're going to go back down to kind of a smaller level and look at the actual bonds that occur inside chemicals here. So chemical bonds are actually really energy relationships between electrons of these different atoms. And the chemical bonds are not actual physical structures. Really, we're going to be talking about these kind of sharing of electrons. And the electrons are really driving our chemical bonds. They're those, especially those electrons in the outer shell, what we call the valence shell, are really going to be what's driving these chemical bonds, which is so ironic because they're so tiny that we don't even consider them in the overall atomic mass. However, they're so important that they're going to drive bonding. So they determine whether a chemical reaction will take place, and if so, what types of chemical bonds are going to form. So when we look at electrons, electrons occupy areas of what we call around the nucleus called an electron shell. So remember I talked about, we like the planetary models, but really electrons aren't just here and here, they're in this electron cloud all around the nucleus, okay, in what we call the electron shell. So electron shell is really that clouded area where the electrons spend most of their time. And each shell contains electrons that have a certain amount of kinetic and potential energy. So the shells are also referred to as these different kind of energy levels. And what really is most important to us is, especially for us here in human anatomy, is that outer shell. The electrons that are in that outer shell, what we call the valence shell. And you'll see that in just a minute, the valence shell. Okay, and that's because that is going to drive how atoms are going to bond with each other. So depending on its size, an atom can have, up to 7 electron shells. We're really going to primarily be dealing with these first 3 shells. And so when we talk about each of the different shells, as we add electrons into that electron shell, the shell that's closest to the nucleus here is going to fill first, okay? And then we'll fill the next shell that's a little bit further away, and then the next shell. So again, we're really going to primarily talk about these first 3 shells because the elements that we're going to talk most about in terms of chemical reactions are going to be in those categories of those first 3 electrons in those first 3 shells being filled. So shell 1 is only going to be able to hold 2 electrons. Shell 2 is going to hold a maximum of 8 electrons. And shell 3 is going to hold a maximum of 18 electrons. However, this electron shell is actually split up into these kind of suborbitals, and the one that's the closest is going to hold 8 electrons. So we're really going to deal primarily with these shells and this portion of the shell, first suborbital of the shell that's going to require 8 electrons. So the easy kind of way to remember how we actually kind of put and design the periodic table based on how many electrons fill that outer shell. So here we only have 2 elements on this row, right? So that's because it has all of these guys have a full outer shell, okay? So that's because we only need 2 electrons to fill that first outer shell. Now the second outer shell, okay, is going to have 8 more electrons. And so then that second shell is full with those 8 electrons. So again, neon here has a full first shell and a full second shell. Now that third shell, as we talked about, really has a total of 18 electrons in it, but remember we talked about there's like these little suborbitals, and that first suborbital of that third shell likes to have 8, and this is all we're going to deal with, okay? So you can see here, sodium has 1 electron in that outer shell, okay? Because again, it's got, again, 11. If you look at a neutral sodium, it has 11 protons and 11 electrons, which means it has 2 electrons in its first shell, 8 in its second shell, and then 1 extra one, right? Because that makes 10, then 1 extra one in this third shell. So it only has 1 electron in that third shell, and it really wants to have 8, okay? And that's going to be important because we're going to talk about things that sodium does, okay, to try to have a full outer shell. Magnesium only has 2, right? So it's pretty far away from having a full shell. Aluminum 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, and argon has 8 in its outermost shell, okay? So now, all of these guys are actually what we call the noble gases. And that's because they have full outer shells, which means that they are high and mighty and noble, right? If we could draw these guys, these are the noble gases. We could give them their little crown here, because they are happy with these outer shells. Their outer shells are full, and so they don't really need to interact with anyone else because their outer shells are full. So that's why we call them the noble gases. They're these high and mighty elements that don't need to interact with any of these other elements, these lesser elements, right? Because they have a full shell, they're happy. So again, that outermost electron shell is called your valence shell, and the electrons in that valence shell are going to have the most potential energy because they're the farthest away from the nucleus, and they're what's going to drive our chemical reactions. So we have what's called, again, I kind of already gave you the octet rule, the rule of 8, but atoms desire to have 8 electrons in their valence shell. And they like to fill that outermost shell with 8 electrons if they can, with the exception of that first shell. And that first shell only has 2. That's the one exception. So they have this desire to have 8 electrons in that outer shell after the first one. So the noble gases, again, already have these full 8 valence electrons in their outer shell, okay? So again, except for helium, again, helium only needs 2 because it only needs to fill that first shell. So our noble gases, just like I talked about, are not chemically reactive. They don't like to interact with other things, so they don't need to. They have full shells and they're happy, right? The noble gases are, we like to call them chemical nirvana. They are, again, happy with their full shells. Now, most atoms don't have full valence shells, and so they're going to either want to gain, lose, or share electrons to be able to achieve the stability of those 8 electrons in their valence shell. And to do that, they're going to have to interact with atoms of either the same element or another element. So this is just showing you the chemically inert elements. These are, again, the noble gases that have the full shells. Helium has a full outer shell with 2 electrons. Neon here has 10 electrons. So it has 2 electrons in the first shell, 8 in the second. That outer shell is nice and happy and full. Okay, so those are the noble gases. But again, most of our elements are not happy. They're left kind of feeling unfulfilled. Like here, hydrogen. Hydrogen only has 1 electron here, so we would really like to interact with another element, share another electron, either share an electron or gain an electron so that it can have that full outer shell. So again, it just needs 1 more electron. Now, carbon here has 2 electrons in this first shell, fills that shell first, but the second shell only has 4 electrons. And so based on the octet rule, it would like to have 4 more electrons in that outer shell before it could be happy, right? Oxygen here has 8 electrons. So again, this first shell has 2, the second one has 6. So again, it would like to have 2 more based on the octet rule, right? It would like to have 2 more electrons to have that full outer shell. And then sodium here has 11 electrons, so 2 in the first, 8 in the second. So it's got a full second shell, but look, it only has this 1 little measly electron, okay? And we're going to talk about that because sodium is going to want to give up that electron because, look, taking on 7 electrons is just near impossible, right? But to give up that 1 electron and then have a full second shell is pretty easy. So there are these 3 major types of chemical bonds: ionic bonds, covalent bonds, and hydrogen bonds. And so when we talk about these types of chemical bonds, we're going to talk about forming our covalent bonds here. We're going to talk about forming ionic bonds where we give up or gain an electron. So, let me advance here. So our first bond that we're going to talk about is an ionic bond, forming ions. And ions are going to be atoms that have either gained an electron or lost electrons to become a charged now atom. And the number of protons is not going to equal the number of electrons because it's either going to take on an extra electron or give up an extra electron. Okay, so we're going to take a neutral atom and it's either going to lose an electron or gain an electron, kind of like we just talked about with sodium. So sodium, again, chloride is going to be a perfect example of this. So ionic bonds, again, are going to involve the transfer of one of those valence shell electrons. And sometimes, okay, that atom will gain an extra electron. So if it gains one or more, sometimes it gains 2 electrons, it's going to become negatively charged. And we call that ion, when it becomes negatively charged, an anion. And I put a picture of an onion here because everybody always kind of has trouble remembering these. So I'm not a big fan of onions. I have kind of a negative association. I'm actually allergic to them. So I have kind of a negative association for them. This may not work for you, but for me it works. And so I think of anion, onion, negative, okay, if that works for you. Then a cation is going to be an atom that actually loses an electron. And so if it loses one of its electrons, it's going to have an extra proton, right? In terms of, I shouldn't say an extra proton, but it's going to have one more proton than it does electrons. So for example, if it had, if it had 10 protons and 10 electrons, and then it just gave up an electron and only has 9 electrons, now it's going to have a positive charge. So we call that a cation. And I always think of, cute cats. Cats is positive. So cation has a positive charge. Now, the other way that you can remember this is that cation has a T in it, which looks like, right, the positive charge. So that's another way that students remember cation as being a positively charged ion, okay? And so what we find then, of course, what forms our ionic bonds is when we have a cation, a positively charged atom, come in contact with an anion, a negatively charged atom, and of course opposites attract, opposite charges attract, and it results in what we call an ionic bond. An ionic bond is a bond formed based on attraction, okay? So for example, if we look at sodium here, sodium has 11 electrons. Remember that outer electron shell, it's stuck with this 1 electron. Like, dude, there's no way it's taken on 7 electrons, right? So its easiest bet to have a full outer shell is to give up that electron. So sodium comes along and it meets its soulmate here, chlorine, right? And chlorine is just the opposite situation, right? With 17 electrons, it has 7 electrons in its outer shell, okay? And so what happens is sodium's like, hey, dude, you need 1 electron to fill your outer shell. I need to give up this electron so I can fill my second, at least my second shell will be full, right? So my outermost shell will be full. We'll both be stable. Perfect, right? So that's exactly what happens. Sodium is going to transfer its electron over to chlorine, okay? When that happens, now chlorine is going to take on an extra electron. It'll have 18 electrons, giving it a negative charge, okay? Now sodium, as it gives up that electron, it's only going to have 10, right? So it will now have one more proton than it does electrons. So that's going to give it a positive charge. So sodium becomes a cation, chlorine becomes an anion, and of course, these two are attracted to each other because opposite charges attract. So this is called an ionic bond, okay? And it's formed solely based on this transfer of electrons and the attraction between the negative and positive charge, okay? So again, I know this is kind of a review, but as you go through this is kind of, you can use the trends for kind of ionic charges in the periodic table here, because when you talk about something like, lithium here, beryllium, or sodium here, sodium, right? We're going to talk a lot about sodium and magnesium here. Sodium and magnesium only have 1 or 2 electrons, sodium 1, magnesium 2 electrons in their outer shell. So, sodium's going to really be much more likely to give up that electron and form a positive charge. Magnesium is going to be, again, much more likely to give up those 2 electrons to have a full second shell, and it will form magnesium with a positive 2 charge, okay? Same here over here. You know, these guys have 7 electrons in their outer shell. They want to take on one more. So they're most likely going to, again, have a negative charge. So again, just kind of how you can use the periodic table to tell you how things are going to bond and what types of ions are going to form. Again, not necessarily super important that you know that, but it's a nice reminder so that you can kind of remember why these atoms are going to form the ions that they do. Now, most ionic compounds are what we call salts. And when dry, salts form crystals instead of individual molecules. So, for example, you know, we've got sodium chloride, right? And so we've got sodium ions that are attracted to you know, chloride ions based on this attraction of charges. And so we can form these nice salt crystals. Now we'll talk about what happens when we dissolve sodium in water. We can kind of physically dissolve these and take these ions so that they'll interact with water molecules if we physically mix it up. So let's real quick, we'll talk about covalent bonds and then we'll stop here and I'll end the lecture. We'll start and pick it up next time. So covalent bonds are actually formed by the sharing of 2 or more valence shell electrons between 2 atoms. So we can share, you know, 2 electrons, one from one atom shares with the other one, like you see here. So for example, hydrogen and hydrogen, right? They both have 1 electron in their outer shell. They would like to interact with each other so that, and they could share, like, so this hydrogen will share an electron here, and this hydrogen will share an electron here. And then they each have, you know, a full electron shell with 2 electrons in it. So that's called a covalent bond. A covalent bond is where you're sharing electrons. If you know, each share 2 electrons, so a total of 4 electrons is shared, then we form a double bond. And if we each atom shares 3 electrons with the other one, so a total of 6 electrons shared, we have a triple bond. Now, this allows each atom to be able to fill its valence shell at least part of the time. And so, again, this makes each of those atoms happy. Now, there are 2 types of covalent bonds. There's equal sharing and unequal sharing. So there's non-polar covalent bonds, which is going to be our equal sharing, and then polar covalent bonds, which is unequal sharing. We'll talk about that. So let's first just kind of go over a demonstration of covalent bonds themselves. So here, if you look at each of these hydrogens, right, have 1 electron, and they would like to have 1 more. They'd like to have 1, they want 1 more. They want 1 more here, right? And here, poor carbon, it only has 4 valence electrons, so it would like 4 more. So what these guys do is they get together and they share. This hydrogen's like, look, I'll share this electron with you if you share this electron with me. Hydrogen's happy, carbon's happier, but not happy yet. And then all of a sudden, oh, this hydrogen shares an electron here, and this hydrogen shares an electron, and this one shares an electron. And so now carbon, right, is sharing, it gets these 4 extra shared electrons, so its outer shell is full. Each hydrogen here is sharing an electron, so its outer shell is full with 2. So again, they're all happy, right? We have a nice marriage of happy atoms here. And so this actually makes methane gas, CH4. And so this is a way that we can kind of structurally show these shared bonds. Shared bonds, again, we oftentimes draw a line between these shared bonds. We don't do that. We don't draw any lines for, like, if we're going to do sodium chloride, which is an ionic bond. We don't draw any lines. Oftentimes we just do this. So here, oops, sorry, I meant to make that a positive. And then chlorine negative. Oftentimes that's kind of how we show, sorry, let me try this again. That's really, again, I apologize for my pen skills. So oftentimes we'll do sodium. Let me try with my pen here. Positive, chloride, I don't know if this is much better, is negative. So again, it shows that attraction, that ionic bond based on attraction. Here now, we oftentimes draw lines between our chemical symbol to show the covalent bonds of a compound or a molecule. Okay, so here also you can take oxygen atoms, two oxygen atoms. They each have, if you remember, 6 electrons in their outer shell, right? So they each need to take on 2 more. So this oxygen atom will share 2 with this oxygen atom. And now that you can count up all their shared electrons, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen atoms happy. And then here, 1, 2, 3, 4, 5, 6, 7, 8. That oxygen's happy because they're sharing these electrons with each other. And so we draw that double bond, right? We show that structural formula with a double bond, 2 lines there. Nitrogen will actually form a triple bond here. And so you can see that they're going to share 6 electrons between them. 3 from this one, we'll share 3 with this one. And we again show that structural formula with a triple bond, 3 lines. So lastly, covalent bonds. Really quick, I'm going to talk about polar and non-polar covalent bonds, and then I'll start off with this one last time. But just to really quickly introduce it, non-polar covalent bonds are where you have equal sharing of the electrons, okay? So nobody's a bully. They're each sharing equally. So for example, hydrogen does this here. Each electron is shared equally. They're spending an equal amount of time with each partner, right? So everybody's happy, and this results in an electrically balanced non-polar molecule, okay? Carbon dioxide is one of these. So again, these electrons here are going to be equally shared. They're going to spend an equal amount of time around the oxygen as they are the carbons, okay? Now, polar covalent bonds results from the unequal sharing. And this is usually because you have an atom that really has a strong pull. Okay, they're what we call very electronegative, that really strong pull on those electrons. And those electrons are actually going to spend more time with one atom than they are with the other. So for example, here, if you have a chlorine and a hydrogen, right? Chlorine needs 1 more electron to fill its outer shell and make 8. And hydrogen needs 1 more electron to fill its outer shell, make 2. But chlorine is going to be the bully, and it's going to take those shared electrons, and those shared electrons are going to spend more time with the chlorine than they are with the hydrogen. And that's going to give this chlorine kind of a partial negative charge, and this hydrogen a partial positive charge, okay? Because the electrons are going to spend more time with that chlorine here. So this results in electrically polar molecules. And we'll talk about this, especially important with oxygen. Oxygen does this as well. Oxygen acts like the chlorine here, and it's going to be the bully and pull the electrons from the hydrogen. So again, this is going to create these kind of partial negative, partial positive. Again, just partial because you're not transferring electrons. It's just they're unequally shared. Okay. So we're going to talk about this. So next time we'll start off with water molecules and talking about these polar covalent molecules, because water molecule is going to be the biggest polar covalent molecule that we're going to talk about, of course, because it's the solvent for most of the solutions in our body. So again, we'll start off here. If you have any questions on what we've talked about up to this point, please send me an email, and I'm more than happy to help you out.